In this lecture, I'll explain domains for functions of several variables and also the limit laws as they are written for functions of several variables. For the domains of a function of several variables, you look for exactly the same things that you looked for the domain of a function of one variable. The rule that you can't divide by zero still holds, so you must exclude any points that would make you divide by zero. The functions we're talking about here are real valued functions, so the domains must exclude even roots of negative numbers, so you end up losing whole intervals. Any numbers that would cause you to have a square root or fourth root or an eighth root or sixth root of an even number, of course those would be imaginary numbers, and those are excluded because the functions are real valued functions. If the functions were complex valued functions, which is perfectly acceptable, but they'd have to be defined for that. But if they are complex valued functions, then you don't have to worry about this limitation. You still can't divide by zero though. And also the domains have to be tailored for your transcendental functions. For example, log is not defined for zero or for any negative number, so you must exclude those from the domains of transcendental functions. So here's an example for a rational function in three dimensions, x, y, and z. So it's a three-dimensional function. Well, looking at the denominator, of course, you can't divide by zero, so that means x squared plus y squared plus z squared cannot equal 25, or you would have a zero in the denominator. Think about what that looks like. If you have, here's my three-dimensional space, x, y, z. Okay, x squared plus y squared plus z squared equals 25 is a sphere of radius 5. Of course, I'm only drawing 2 dimensions of it, but it does have, all 3 dimensions. That means the function is not defined on this entire sphere in this of radius 5. That's kind of interesting. Okay, now looking at the numerator, you see a square root, and of course you can't have the argument of the square root be negative, so x cannot be greater than 6. So here is the domain of this function. F, it's a set of all x, y, and z such that x squared plus y squared plus z squared is not equal to 25. That will give you that sphere, exclude that sphere. And also x has to be less than or equal to 6. Now here's an example for a transcendental function, natural log of x over y. So we start right off and say you can't divide by 0, so that means y cannot be 0. Y of equal to 0 is already excluded from the domain. But now logarithms are not defined for 0 or for negative numbers, so to avoid having a 0, x had better not be 0 either. Now to avoid a negative argument, you want the signs of x and y must be the same. Right? Because if y is negative and x is positive, then you're trying to take the log of a negative number, and the other way around, if x is negative but y positive, again you'd be trying to take the log of a negative number. This actually ends up giving you only the first and third quadrants to worry about, but here's the domain. Domain is a set of x and y such that x times y is greater than 0. That includes all of this statement. X can't be 0, y can't be 0, and the signs have to be the same. Now when you get to a multidimensional function, the limits get very complicated. Or rather, determining the limits can be very complicated. Recall that in one dimension, you had to worry about the right-hand limit and the left-hand limit. I mean, one-dimensional domains, of course. So if you have a function like this, you have to worry about, if you're at this point, you have to worry about the limit as x approaches from the left, and also as x approaches from the right, or coming down the function, you had to worry about those two. And that's all you had to worry about. When you get to where, and then two space meaning two space for the domains, when you get to functions of several variables, the idea of right and left hand limits really becomes something almost intangible. You have to show that the limit along all lines of approach to the point are the same. course, at boundary points, you only have to have every line as it approaches from inside the domain. If we're looking at the point 2, 3, and so this would be a function of x and y. I'm not showing the values of the function, I'm just showing the domain in the x and y plane of the domain. Okay, but here are the lines of approach. Instead of just right and left hand limits, remember now you would have all these straight lines that are kind of shown in green. So all these straight line approaches, and of course there's an infinite number of them, but also these lines that are curved. See this kind of yellow ones? They're curved. Here's this red one, it's curved. This yellow one is parabolic. Here's another parabola, but it would have any dimension, any line of approach to the point 2, 3. The limit has to be the same along every line of approach in order for the function to have a limit at the point 2, 3. So to do this, you must use algebra and some tricks to show that the limit exists and that it is the same along all paths of approach to the point. If you want to just show the function doesn't have a limit at the point, all you have to do is show just 2 lines of approach. You don't have to disprove it along every line. So if you're very clever and you can figure out 2 lines where the limit will be different, then you're done. As in functions of one variable, we have limit laws for functions of several variables, and they're exactly the same limit laws, and you can use them. Also, certain functions that you're familiar with as far as being continuous, as far as having limits in one dimension, also have them in higher dimensions, for example polynomials and exponentials. So here are the limit laws. We'll have 2 functions f and g, and they have limits L and m respectively. That means they already have their limits. You can't use a limit law to prove that f and g have limits. They already have to have limits in the first place. I think I said that twice. Okay, so let's say the limit as, and I'm using 2 dimensions to show you. Of course, you can have functions of higher, from a greater number of variables. It'd be the same thing. So you're taking the limit as at the point x naught y naught. So let's say at the point x naught y naught, f has a limit L. At the same point, g has a limit m. Then here are the limit laws, and you're pretty familiar with them. But notice what I do. Sometimes in the book, they write a limit law for the addition of the functions, a limit law for the difference of the functions, and a limit law where the function is multiplied by a scalar. It's more common to write all these as one statement, because that's a statement of linearity. Alpha f plus beta g, so all you have to do is write plus, because beta could be negative. That would take care of the negative. Here you've got the alpha and the alpha beta. You already have the scaling of the function, and this is all written in one statement. Alpha f plus beta g equals alpha times L plus beta times m for all real alpha beta. The others are written separately. Here's a multiplication rule. Here's a division rule, as long as the whatever you're going to divide by doesn't have a limit of 0 at that point. Note that if it's 0 over 0, you can consider using L'Hopital's rule. And also we have a limit law in terms for the powers. In the first 2, I think, problems in the homework under finding limits, I suggest you use the limit laws. And here's an example of how you do that. This is a polynomial. F is a polynomial. I know it's continuous, even in higher dimensions. And at some point, let's say 2, 3, and 0.2, remember I've got to have 3 values here. This function, f, has a limit of 30. Here's g. It's exponential, and its limit is 3.32 at the same point. So this is L, and this is m. Now here's a statement or an example of the linearity. Remember, the linearity was alpha times f plus beta g. The limit is alpha L plus beta m, and that's what you're seeing here. So this becomes 6 times L, which is 6 times 30, minus 3g, which is minus 3 times 3.32. And so now you have a limit for that particular combination of f and g. If you multiply f and g together, you just multiply the limits. Dividing, you just divide the limits.